Okay, uh, let's start. This is the fourth class, okay, that we're doing. Uh, on Wednesday, I started with discussing the geometry of LP. So today I want to continue with that discussion. I want to cover a few more topics which I think are relevant, and then this will lead us into the simplex method, which we will develop next week, and I will go through all the ideas in simplex next week. Okay, so I want to start by just recapping, and maybe if you've got questions you can ask me from anything from last class before we start for today. So just a quick recap from last class. Okay, so a couple of things. So our topic was geometry of LPs. So we were trying to understand specifically this concept of polyhedron. We were trying to understand properties of polyhedron. Okay, and of course our goal is to do this towards studying to solving linear programs ultimately. Okay, so a few definitions. So one definition which I discussed last time was this notion of convex hull. Okay, which is an important concept. Okay, so the convex hull of a set. So if I give you a set, now this could be a finite set of points. So let's say I've give you a finite set of points. So this is the set X. Okay, all these points are, so there are 1, 2, 3, 4, 5, 6, 7 points. The convex hull of this set is basically given by all convex combinations of these points. Okay, and if you were to visualize this in if you were to visualize this in 2D, how it would look is, it is another way to think about this is, think of the smallest convex set that contains all these points basically. Okay, so actually if you plot the convex hull of this set as capital X, if you were to plot this, the set actually would be this. Okay, so this is the convex hull of the set X. Okay, and we define this, the definition of the convex hull of the set X. Okay, again, this is recap from last class. The definition of the convex hull of a set X is all points X such that X is given by some convex combination of these points, xk, where xk lie in the set X for all k. Okay, these lambda k's are non-negative for all k, and they add up to 1. Okay, and you can check this for, I mean, you can choose uh, any number of points basically. So you can take any convex, so you can take any set of points here uh, in the set X. You take a convex combination that's given by a point. If you take the set of all convex combinations, that will look like this basically. Okay, so this should be maybe k greater than equal to 1. Okay, so this is the definition of a convex hull. Okay, any questions with this definition? This set is going to be critical in many ways. Uh, of course, for linear programming, the convex hull is an easy object. It's going to be a polyhedron. When we come to integer programming, discrete optimization, the name of the game there is to try to characterize the convex hull of the set. Because if you, and we will come back to this later, but in discrete optimization, it's going to be a much harder optimization problem to solve. And a big key challenge there is to represent the convex hull of the set nicely. And it just turns out for some sets you can do this, and some sets you can't do this, which is why integer programming is not is a trickier much trickier problem. Okay, okay. So that's one definition. So we saw the definition of the convex hull. The second definition, which I did last time, was this notion of uh, three notions basically. So I spoke about extreme points, vertices, and basic feasible solutions. Okay, so we did this last time too. And if you think about this convex hull of this set, in this case, this is a polyhedron. Okay, so in this example, this is a polyhedron. In fact, it's a polytope. It's a bounded set. defined by, in this case, 1, 2, 3, 4, 5 linear inequalities. The extreme point is simply a point such that you cannot write it as a convex combination of two other points, basically. Okay. So if I'm looking at the set blue, if I'm looking at the blue set now, so if I'm looking at the LP region, so the LP region, so this is the LP region. All this is my feasible region of a linear program. So for this LP, this point is an extreme point because I cannot take two other points in the set which are different from this and write it as a convex combination. Okay. While this is not an extreme point because I could take two other points and write it as a convex combination of these points which are distinct from this point and they lie in this set. Okay. So this is my polyhedron basically. Okay. So this is an extreme point. This is also an extreme point. This is also an extreme point. Okay. All of these are. So there are, in this example, there are actually 5 different extreme points. Okay. What's a vertex? A vertex was a point such that I can find it to be a unique minimizer over this polyhedron or polytope. So in this example, if I take this particular point, I can choose it to be, so if I just remove these lines, I can choose it to be, I can find this point to be a unique minimizer simply by choosing an objective function, which let's say is increasing in this direction. So let's say I'm minimizing, this will be the optimal solution and it's a unique solution. Likewise, if I take a point like this, I can identify a direction or an objective. If it increases in this direction, the objective function, then these are all points with the same objective function value, then this will be a unique minimizer. So each of these points, I can actually find it to be, I can identify an objective function so that it's a unique minimizer. That's the definition of a vertex. So each of those 5 points also become a vertex. Okay. So this was a geometric definition. This was a optimization viewpoint. I can find an objective function, a linear objective, of course. Okay. So that it's a unique minimizer. And then the last definition was this definition of basic feasible solutions, which was an algebraic definition, which simply says that if you take a point which is in the feasible region, at this point, there should be n constraints which are linearly independent and active at that point, basically. Okay. So if you take this point, all this means is if you take, so firstly, this point is clearly feasible. Okay. It's clearly lying, it's satisfying all the constraints. At this point, this constraint and this constraint are active. Two of them are active and they are linearly independent because if you solve for these two equations, you will get this point to be the unique solution. So basic feasible solution simply says that you should have n in dimension n. So this in dimension 2, you should have n constraints which are linearly independent and are active at that point, and that point has to be feasible. Okay. Otherwise, it's not a basic feasible solution. Okay. So this was important because the what we will work towards is for any LP, there will always exist an optimal. If there is an optimal solution, there will be one at a basic feasible point. And so we will be searching for the basic feasible solutions in the algorithm. Okay. Okay. So this is from last class. Are there any questions or any concepts from this class that are unclear at this point? Okay. So what we'll do next is then, if there are no questions, and again, you can ask me as we go through, we will first, I want to first think about the basic feasible solution, the notion of this. I want to concretize this for a standard form LP. Okay. So let's go back to a standard form LP. Okay. And the reason for doing this is when we do linear programming, when we develop the simplex method, we will develop it for a standard form LP. Okay. So remember, a standard form LP is a LP of this type. You minimize C transpose X subject to AX equal to B and X non-negative. Okay. Again, just to get the dimensions, just to be clear about the dimensions, N here is the number of variables, so number of X variables, and M is the number of equality constraints. Okay. So I want to think about what a basic feasible solution will look like for this particular LP. And again, by studying this LP, uh, because we're going to develop simplex for this, and that's perfectly fine because we know every LP can be written in this form. Okay. Okay. So we're going to make one assumption here, which is really without loss of generality. So the assumption is that the rows of the matrix A are linearly independent. Okay. So this is really without loss of generality. I mean, if you think about you're solving a set of equality constraints, if there is some linear dependence, then you can identify it by simple linear algebra, basically. Okay, so finding linearly dependent equations or linearly dependent constraints is a trivial, I mean, it's a reasonably easy task. Okay, so we're going to assume that these rows are linearly independent when we develop the method. There's no loss of generality here. Okay, and uh, because we have got a set of equations in n variables here, okay? So this will mean that basically the number of equality constraints m will be less than or equal to n, okay? So think about a LP where you have m equality constraints and these m will be lesser than equal to n, okay? And there is really no loss of generality in doing this, okay? Okay. So what is a basic feasible solution? Okay. Okay. So let's define a basic feasible solution. So we have two constraints, ax equal to b and x non-negative in our polyhedron. Okay, standard form. For a basic feasible solution, I require n linearly independent active constraints. Okay, so what we are going to do is we're going to partition. So I'm going to partition the matrix A as, so remember A is a matrix of size m by n. Okay, I'm going to partition this in the following form. I will take a set of columns of the matrix, which will also be of size m. Okay, so this is basically a square matrix. Okay, and I will require this matrix to be invertible. Okay, so this has to be a full rank matrix. Okay, so this matrix will have to be invertible, and then I've got a set of other variables, other columns, which will be of so the number of columns here will be n minus m. So I'm basically just partitioning. I'm going to identify a set of columns of this matrix A, so that the corresponding m by m matrix, the columns are basically linearly independent. Okay, so I've got a full invertible matrix B. Okay, so we have to identify this. Okay, such that essentially B, which is a square matrix, is invertible. Okay, so now if you think about what the constraint ax equal to b tells you, ax equal to b is exactly the same thing as saying I'm going to partition my, so remember every column of the matrix A, so this is matrix A, right? And there's a vector x. Any column of a matrix corresponds to a particular variable x. Right? When you do your matrix vector product, this column, let's say the third column will be multiplied with the third variable. Okay. So every column of a matrix corresponds to a variable. Okay. So I can rewrite this as b times a set of a set of variables. So all the columns so let's say pick this column, and let's say a third column here, fourth column. Okay. So the corresponding first, second, and the fourth variable form my variables xb. These are going to be called basic variables, and the corresponding remaining variables are going to be called non-basic variables. Okay. Okay. So I'm partitioning basically my variables x into two parts. These are going to be called my basic variables, and we will see how we do this. And these are going to be called non-basic variables. Okay. So what do we do? Because we know our matrix B is invertible, I can rewrite this as bxb is equal to b minus nxn, and b is invertible, which means I can rewrite this as b inverse b minus nxn. And now all I'll do is I will force these variables to be 0. Okay. So I will set xn to be 0 which are my non-basic variables. And this will imply that xb has to be equal to b inverse b, which are my basic variables. Okay. So how many constraints are sat? So, I've got a set of, this is in dimension n, right? The total number of variables is n. Okay. So how many, for a basic solution, I require n linearly independent active constraints. How many are there? So I've got m equality constraints, which I'm solving. I'm finding xb by solving the m equality constraints. So there are m equality constraints which are satisfied, which are tight, plus this xn, which I set to be 0, there are n minus m such variables. So I chose n minus m non-basic variables. I made them equal to 0. Set to 0. Remember, my LP has equality conditions and inequality conditions, non-negativity conditions. I get m from here, I get n minus m from here, I get a unique solution to this problem. When I solve this set of equations, essentially I'm finding the moment I set xn to be 0, xb was uniquely determined. So these are n linearly independent active constraints. Okay. So you get a total of n linearly independent active constraints. Okay. So that's a basic solution, right? The only thing I need is for it to be feasible. So I have to ensure that this thing is non-negative. So if xb, which is b inverse b, is greater than equal to 0, then this solution, then basically this xb xn, which is b inverse b and 0, is a basic feasible solution. Okay. This matrix B, there's a name for this. B is called the basis matrix. Okay. And of course, XB is the basic variables and XN is the non-basic variables. Okay. So the idea of a basic feasible solution, we are just contextualizing it for a standard form LP. Okay. Was that clear? I will show an example just to make it concrete. We'll do it with an example. Okay. But is there any step here which is, I mean, maybe we can do an example and then you can, if you've got questions, you can ask me. Okay. Yeah. I'm saying that this implies that there are n linearly independent active constraints at X. How do I know this? I set Xn to be zeros. Okay. And then the remaining XBs are uniquely determined because B is invertible. So there's no other way to find XBs basically. Okay. So we require n linearly independent active constraints at a point for it to be a basic solution. I mean, one thing important, of course, is it also has to be feasible. Okay. And last time we discussed, you can have basic solutions which are not feasible. So you do require this non-negativity condition for feasibility. Only then it's a basic feasible solution. There is no guarantee when I do B inverse B, it will be non-negative. Okay. So let's do an example just to contextualize this. It'll help. Okay. Let's take a simple LP. Okay. I'm just keeping. Let's do it in 2 dimensions. It's the ideas just carry forward. Okay. So what we'll do is, so this is an LP. I'm writing this in not in standard form. So we'll convert this. So in standard form, if I want to transform this, it'll become x1 plus x2 plus a slack variable equal to 6, x2 plus a slack variable equal to 3. Then I have x1 non-negative, x2 non-negative, s1 non-negative, and s2 non-negative. Okay. Okay. So if I was to plot this feasible region for this problem, okay, how will it look? This is x1, this is x2, So x2 is less than equal to 3. Sorry. Okay, so uh, this is x1 non-negative. This is x2 non-negative. This is x2 less than equal to 3. Okay. So another way you can write this is, if you want is, so this is x2 less than equal to 3. And then you've got x1 plus x2 less than equal to 6, which is going to be a point going this way. Okay. This is x1 plus x2 less than equal to 6. Okay. Another way you can think about this is, this line is the line where x2 is equal to 0. This line is x1 equal to 0. This line is the line where s1 is equal to 0. And this line is the line where s2 equal to 0. Okay. Okay. So let's take, so what's a feasible region? The intersection of all these things. So that's a feasible region. So there are four basic feasible solutions. Let's take maybe this one. Okay, let's take this basic feasible solution. Okay, so let's call this point. So this is a basic feasible solution. Okay, let's try to figure out what this basic feasible solution looks like. So there are two variables which are set to 0. So in the standard form LP, what do I have in this problem? I've plotted it in 2 dimensions. But if I look at the standard form LP, n is 4 in this problem, and m is 2. So my number of non-basic variables, so my number of basic variables should be 2, and number of non-basic variables should be 2. So at this point, what are my two non-basic variables? S1 takes a value 0 and S2 takes a value 0 at this point. So my non-basic, so if I call this point A, at the point A, if I set S1 and S2 both equal to 0, my slack variables, if I solve for my basic variables, X2 will be 3, X1 will be 3, which means that my basic, so these are my non-basic variables. This is Xn. My basic variables are X1 and X2, which will take a value in this example of 3 and 3. When I solve these linear equations, I will only get the points 3 and 3. And clearly, at this point, the numbers are non-negative, obviously. So that's a basic feasible solution. Okay. What is the basis matrix? The basis matrix is simply the matrix formed by the columns of the basic variables in the A matrix. So the columns here are 1x1, 0x1, 1x2, 0x2. So my basis matrix will be 1, 1. Sorry, this should be 1, 1, 1, 0, 1. So B is simply the matrix 1, 0, 1, 0, 1, 1. And my non-basic, my matrix corresponding to my non-basic variables is 1, and there is no S2 here. There's no S1 and no S2. There's one S2. So it's the identity matrix 1, 0, 0, 1. And you can do something similar for every basic feasible solution. So for example, if you take, let's take this basic feasible solution. At this point, what are my non-basic variables? Can you tell me? At this basic feasible solution, what would my, what, okay, or another way to think about it is, what two constraints are linear, are active at this point? This constraint and this constraint. If you solve these two equations, this point will be found uniquely. How do you find, what are these two equations? S1 equal to 0. That's this equation. And this equation is x2 equal to 0. So at this point, my non-basic variables are s1 and x2, both will be 0. My basic variables will be x1 and s2. Okay, and you can write down b and n and so on. Okay, any questions? Is it clear, or do you want me to go a bit slower? Can you see for each of these, at every point here, there will be a set of two basic variables. They will change. So here the basic variables will be S2 and X1, basically. Okay. At this point, my basic variables will be S1 and S2. My non-basic variables will be X1 and X2. Okay. At this point, my basic variables will be X2 and S1. Okay. So in this problem, there are the number. So okay, and maybe I should also mention this just for so you guys are all it's very clear. There are also points like this. So there are four basic feasible solutions. Okay, you can have a point like this, which is also a basic solution, right? Why is this a basic solution? At this point, if I was to set x1 equal to 0, and if I set s1 equal to 0, so if I made x1 equal to 0 and s1 equal to 0, okay, I will get this point basically, right? If I set x1 equal to 0 and if I set s1 equal to 0, you will get this point. But this is not going to be a basic feasible solution because this is going to violate the condition on x2. If I make x1 and s1 equal to 0, x2 is equal to 6. This violates the second condition where x2 cannot go too large basically. X2 cannot go beyond 3. So this is a basic solution where the non-negativity condition will be violated basically. That non-negativity of the slack variable is going to get violated. So you have four basic feasible solutions, one basic solution. Okay. So what are you doing? You're basically finding columns. You're hoping to find linearly independent columns in dimension 2 here. Identify all of them and then find all the basic feasible solutions. Okay. Okay. Now here is the first sort of note which is important, which is think about standard form LP. Okay. What is an upper bound on the number of basic feasible solutions? So in a standard form LP, I've got A is a matrix. It's of m rows and n columns, right? There are n columns. What am I doing? The number of basic feasible solutions. What am I doing? I'm basically trying to find m columns here so that the matrix is linearly independent. I mean, it's a full rank matrix. I can invert that matrix out. So I've got n columns, of which I'm trying to find m columns so that is linearly independent. So the total number of possibilities in the worst case will be n choose m. Out of n columns, you pick m. This is going to be n factorial divided by m factorial by n minus m factorial. So this is the first challenge in linear programming. This number as a function of n and m does not grow polynomially. It grows if m is, for example, order of, let's say, n by 2. Let's say I've got 100 variables, I give you 50 constraints. This is 100, choose 50. That's an exponentially large number. Okay. So you cannot so as an algorithm, you cannot think about linear programming. I will enumerate all basic feasible solutions. I will just identify all BFS, find the objective function at each point and pick the minimum. You cannot do this. This is not computationally feasible because this number it's a huge number and it grows exponentially as a function of n and m. Okay. So though you have gone in of course in linear programming there are infinite number of points because all points in this feasible region also can be potential optimum solutions. Even if we restrict to basic feasible solutions, there is an astronomical number, an exponentially large number. So enumerating basic feasible solutions is not an algorithm which will have any good complexity. Okay. So that's why LP is not a trivial task of it's not a you cannot just say I will just write down all basic feasible solutions, I'll just enumerate everything and find the best among them. That's an algorithm. It is not a meaningful algorithm. Okay. Good. Any questions with this? Hopefully, you can contextualize these ideas. You can try it out on your own. Just take some other points and identify the corresponding basis matrix, non-basis. You can do this on your own at your time. Okay. Okay. Any questions, either online or here? Okay. So the next thing I want to mention is, or we should discuss is the concept of degeneracy. So this was raised last time by somebody, but I did not mention this. It's the right time to discuss this now, which is what there's a concept of in LPs, there's something called degeneracy, because what did we say about linear programming? We said that a basic feasible solution, we want that we want that n linearly independent active constraints. Okay. So firstly, you're in dimension n. Okay. You cannot get more than n linearly independent constraints at a point in dimension n. Okay. Degeneracy says so a basic solution X is degenerate. So this is a definition. If there exists more than n active constraints at X. Okay, I'll show you an example very soon. But essentially, if you have more than n active constraints at a point, that's called a degenerate solution. So what's a degenerate basic feasible solution? So degenerate basic feasible solution simply says that a basic feasible solution, because a basic solution need not be feasible. Okay. So basic feasible solution that has more than n active constraints at that point. Okay. Clearly, a basic feasible solution has to have n linearly independent active constraints. So for finding the point, you expect n constraints, but you have more than n constraints which are active at that point. Okay. Constraints at X. Okay. Okay. So I'll show you an example. Okay, let's go back to this example. So let's take the same LP. Okay. Except now I'm going to slightly modify the LP. Okay. So I'm going to give you a slightly modified LP. So I'm going to add in an extra constraint to this LP. Let's say X1 is also less than equal to 3. Okay. So let's say I take this problem now. So my feasible region is changing now a bit. Okay. I've got a third condition, which is, I'm not interested now in this, X1 less than equal to 3. Okay. So what is this constraint? This constraint actually, so this point was the point 3 comma 3. Okay. So X1 less than equal to 3 is a constraint of this type. Okay. So in this problem, so my feasible region has now actually become a box, or a square rather. Okay. I cut off part of my feasible region with this constraint. Okay. Take this point A now. Okay. At this point A, okay, there are how many constraints are active among these? At this point A, so what is the point A? It's 3 comma 3. Okay. At this point, X1 plus X2 less than equal to 6 is active, because 3 plus 3 is equal to 6. X2 less than equal to 3 is active. X1 less than equal to 3 is active. So there are 3 active constraints at A from my feasible region. I'm in dimension 2. Two of these constraints should be enough to tell me what A is. The third one is really just a redundant constraint. It doesn't give me any additional information. If I say I solve these two equations, the third one satisfied at equality happens automatically. Okay. So this is an example. So in this representation, A becomes what's called a degenerate basic feasible solution. Okay, you have more constraints than you might typically expect to be active. Of course, you cannot have three linearly independent constraints which are active at this point. This is not possible in dimension two. Okay, but two of them are sufficient. You have an extra constraint which is automatically getting satisfied. Okay, okay. So this can happen. Okay, so what happens is, and what does this mean for standard form LPs? So in standard form LPs, a degenerate basic feasible solution simply means that, so remember in standard form LP, what do you have? XB is equal to B inverse B, which is non-negative, and non-basic variables are zero. Okay. And I've got conditions AX equal to B and X non-negative. Okay. I've got N minus M constraints which are active here, which are inequality constraints which became tight, and M constraints which were tight from the equality constraints. So I got a total of N active constraints at this point. But if some of my basic variables also become zero, then some of these additional constraints here become tight. So in a standard form LP, a degenerate basic feasible. So if more than N minus M variables are zero, or or another way to say this is a basic variable takes a value zero. That's a degenerate basic feasible solution for a standard form. Okay, when you solve this, so in this example, if I added in a third slack variable, so remember what we did is we converted this, right? X1 plus X2 plus S1 equal to 6 in the standard form. X2 plus S2 equal to 3. And if I added in the third constraint here, a third slack variable, X1 plus S3 equal to 3, of course, I require all my slack variables to be non-negative. What will happen in this problem is, at this basic feasible solution, you will have two basic variables. Okay, because this is in I'm sorry, you'll have three basic variables. Is M in this problem? Now M is 3, not 2. Okay, M is 3 now. 1, 2, 3 equalities, and there are 5 variables. So you have three basic variables. What will happen is, at this point, one of the basic variables will go to 0. So if you take, for example, these two constraints, let's say you take this constraint and this constraint, and you solve it, that means S1 is 0, and this is what? This S3 equal to 0. You solved it, you found this point. But automatically, S2 also became 0. S2 was a basic variable. You will find S2 uniquely, it became 0. Okay, so there are some additional constraints, non-negativity conditions, which also go tight, basically, at a degenerate solution. Okay, now this can happen in LPs, and the challenge is when you have large LPs, degeneracy is an issue which can cause cycling. So what will happen is, we will see this, we'll come back to this in the simplex method. You might think that you're going from one point to a new point, but you might actually stay at the same point. So you have to worry about this in linear programming, in the algorithms. Degeneracy is an important issue in algorithm development in LPs. Okay, so this can affect the numerical performance of algorithms. Essentially, you have more constraints than necessary which are active at a point. Okay. Okay. Any questions with degeneracy? Is this clear, or should I go slower? Any questions online? So I do want to make a note that degeneracy it's not a, it's not a, so do not think that it is just a, it's a mathematical, issue, and, we don't worry too much about it. Actually, degeneracy affects um, numerical performance of algorithms, especially the simplex type method can get affected by this. Numerical performance of algorithms such as simplex. We have not seen the simplex method as yet to solve LPs, and so you have to be we have to we'll have to deal with this and think about this when you develop algorithms. Okay, how does it affect it? We'll see next time. But you can have this issue of what is called cycling. Okay, we'll come back to that later in the simplex method. But essentially, the idea is that you might think that, okay, like there are more than necessary constraints which are active. So if you take any two constraints, you're getting the same point, but then you try another two constraints, you got the same point. You're not moved basically. Okay, you stayed at the same geometric point. And if this is not optimum, you need to, yeah, you need to deal with this. Okay. Any questions? Okay. Okay. So what we will, so the, okay. So we defined basic feasible solutions for standard form LPs. We showed equivalence of BFS, extreme points vertices. We now want to work towards this idea that for a LP, sorry, there's a question online. Let me just check that if you don't mind. How do you know there are too many constraints? Is there a rule for this number? So there's a question online. How do you know there are too many constraints? Is there a rule for this number? So the rule is simple. If I'm solving an LP in n variables, at a point, I don't know. So firstly, the concept of degeneracy relates to a point. Okay. Like this is a degenerate basic feasible solution. This is a non-degenerate basic feasible solution. Okay. So you can have degenerate and non-degenerate basic feasible solution. So this is a non-degenerate BFS. So how you would know something is a degenerate solution is a basic feasible solution is that point is feasible. N constraints are linearly independent and they're active. I mean, they're satisfied at equality, but there are some additional constraints which are also satisfied at equality. So you have to just count. Okay. So if I give you a point and I give you all the constraints, you check all the constraints and you check more than N constraints are active at that point, basically. Okay. So if you're on 100 variables, more than 100 constraints are active at that point. Okay. So hopefully that answers the question online. Okay. 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 So what we want to work towards is, so I want to work towards the claim that for LPs, we can restrict attention, or we can restrict finding the optimal solutions to only basic feasible solutions or extreme points. Okay. We haven't officially shown that. We haven't formally shown that as yet. We have seen that with figures in 2D. I haven't shown it to you in 3D too. You can try it in 3D. But we need to have an argument that why can you restrict in linear programming a solution to only an extreme point? Okay, you cannot do this necessarily for other types of optimization problems. Okay, so I can create, so if you take an LP like this, I my claim is you can only focus on these 3 points for optimal solutions. You don't have to worry about other points. Okay, this may not be the case. So for LPs, you can restrict to these points, but you can have other types of problems. For example, let's say my let's say this is my feasible region, and let's say I've got an objective function like minimizing x1 squared plus x2 squared over this feasible region, the same polytope. So remember, this is a linear program, right? It's the same feasible region. Okay, it doesn't matter what. Okay, if I try to minimize a linear function, my claim is you can only focus on these 3 points for LPs. This is a quadratic program. It's a quadratic function. If this is the origin, it's very clear what the optimal solution is because this is a non-negative number. Optimal solution can only be the origin. So in a quadratic program of this type, the optimal solution will be in the interior. Any of these points will not be optimum. Okay. So for linear programs, you can restrict attention to extreme points. This we need to make concrete. At least we need to have an argument for this. Okay. This is not true for general optimization problems, right? In this case, the optimal solution is here. It will be the origin, right? For this quadratic program, this is a QP. This is an LP. Whatever C1 and C2 you choose, I claim you can restrict attention to one of these 3 points. Whatever. Okay. So let's make that clear. Okay. Is that clear, this figure? Was it confusing or? I mean, my point is we are proving a theorem for LPs, but that's no. It is not going to translate into all optimization problems. Okay. So just be mindful. Okay. That's why we have to prove it for a class. Okay. Okay. So let's do this. So I need a definition of, okay. So we need to have a characterization of if a polytope has an extreme point. Okay. So it turns out, so lines and extreme points. Okay. So I showed you I showed you a figure here where the notion of, you can just visually, it's clear these three are extreme points or corner points. I can create polytopes where there is no corner point. Okay. So for example, if I take a polyhedron, which looks like this, these are supposed to be two parallel lines. So sorry, it's hard for me to draw parallel lines. So let me just cut and paste. So let's take this line. Where is the point going? That's where the plot is. Okay, so these are parallel lines. Okay, let's say my feasible region is the intersection of these two parts. So this feasible region is all this space. Okay, it's clear that for this feasible region, there is no, there is no notion of corner point, right? That's what a corner point means. Things have to, there has to be there should be like, and that in 2 dimensions, no point here will have more than one constraint which is active, right? Only one constraint is active here. No constraints are active in these points. Only one constraint is active here. So there are polyhedron which may not have an extreme point. You can create this. Of course, there are polyhedron which will always have an extreme point, right? Like the example we saw. So here's another polyhedron. This might be unbounded, but that is an extreme point here. Okay, so P, there is no extreme point here, but it is a polyhedron. Q has an extreme point. It's also a polyhedron. Okay, so what does it mean to have an extreme point? This result we won't prove, but I think it's quite intuitive. So a polyhedron P, so any polyhedron P contains a line. So what's a line? A line is if there exists some point x which lies in P such that x plus, if there exists a point x in P and a direction D, so a non-negative vector D in Rn, such that x plus lambda D also lies in P for every lambda in R. Okay, so that's a definition of a line. Okay, and it's very intuitive. If you can find me a point and a direction, so this is a point and this is a direction, I can go arbitrarily in this direction and in this direction. So this is positive lambdas, let's say, and this is negative lambdas. For every lambda, I can go along this line, along this direction and say feasible. That's a line. Clearly, here I cannot do this because if I take this direction, at some point I move out. If I take a direction in this way, if I take a direction in this way, if I go in this direction, at some point I move out. Okay, so this has to be true for every lambda in R. And of course, the definition is this direction has to be non-negative or non-zero. Otherwise, a trivial definition. Okay. So I think it's clear what a line means, and it should be clear that a polyhedron will have an extreme point if there is no line. If there is a line, okay, this notion of a corner point will not exist. Okay, so this is, I think it's, I'm not going to prove this, but this one I think is a easy observation. So for any non-empty polyhedron, P, P has an extreme point, which means it has a vertex, it has a basic feasible solution, if and only if P does not contain a line. Okay. This one I'm not going to prove, okay, but I think it's geometrically, it's quite straightforward to see. Okay, I believe. Okay. So what we want to now argue is, okay, so of course a polyhedron can be empty. Okay. If a polyhedron is an empty set, then of course this problem is not interesting. Okay. But if you have a non-empty polyhedron, it has an extreme point if and only if it does not contain a line. So for example, take any bounded polyhedron. So take any polytope. Every non-empty polytope, every non-empty polytope has an extreme point. This has to be true because what's a polytope? A polytope means that the x values are bounded from above and below by some integer. So you cannot go arbitrarily in some direction and increase it, right? If x plus lambda d, if lambda goes arbitrarily large, at some point you'll violate this constraint. So every non-empty polytope has to have an extreme point, right? Clear? Similarly, every uh, uh, every standard form LP, standard form LP with non-empty feasible region has to have an extreme point as an extreme, not polytope, as an extreme point. Okay. As an extreme point. So again, when you work with standard form LPs, if it is feasible, there will be an extreme point. Why is this the case? Think about standard form LP. AX equal to B, X non-negative. If I want X plus lambda D to be in the set, at some point, this is going to violate the condition because this has to be true for every lambda. So if some direction vector is this direction vector is non-zero, at some point for either lambda being very positive or very negative, this condition is going to get violated, right? So if d is positive, at some point if lambda goes very negative, this is going to get violated. Likewise, if d is negative, the component, at some point if lambda gets very high, it's going to get violated. So this cannot be true basically for lambda. So because of this constraint, it lies in the non-negative authent basically. So you cannot have a line going through indefinitely, so it has to have an extreme point. Okay, of course, all these results are if it's non-empty. Okay, I can create empty feasible regions for LPs. Okay, okay. So what we will do after the break is I will argue that for a LP you can restrict attention to a standard to extreme points, and then we will do a couple of more algorithmic ideas for LPs for polyhedrons after the break. So it's 10:57. We will start by in about 5 minutes. Okay, let's take a break. Read okay or slightly fast?
Slightly fast, yes.
You're doing this course as a, are you a master's student or
Yeah.
you're doing this course for what? Like, what's it?
Yeah. My one of my colleagues and then it's just looking at said,
What are you working?
I'm here to publish.
Ah, okay. So you're doing master's by research.
It's good
So you need to do coursework for the program.
for research.
I think PhD students have coursework requirements. Masters by research students, you have requirements.
Interesting check out
Research, right?
research.
So this you're doing this out of this.
I don't this is by my company. It's invested.
No, I mean the coursework.
Oh, the coursework.
Is it part of your requirement
It's other.
for a PhD for a master's program? I mean, it's new.
Uh,
So you have some requirement on how many master's classes you have to do.
yeah, no, so it's my master's is two form modules, two personal development. It's professional development modules.
I see.
Yeah.
Because this class have targeted it at the I do proofs and stuff like that. So it's of course, you know, I took this class I was a master's student. But yeah. But I did not realize that master's students have the requirement to take PhD. I mean, it's in the sense that it's perfectly good, but well, master by research, I can just write research. We just focus on research.
Oh no, we have to check one.
So you have the course requirement.
Yeah.
I understand.
Because previously I did optimization so for data science.
I see.
I said first.
With Antonio.
Ah yes.
Okay. Okay. You guys okay? Okay. Just okay. Okay. So maybe we'll start. Okay. Uh, so let's see the student back. Okay. So I discussed the notion of when a polyhedron has an extreme point if it does not contain a line. So what we are going to argue next is here's a theorem. Some background noise. You can mute yourself. Thank you. Okay. So here's the theorem that we will try to argue next, which is or not argue but prove next, which is so given an LP, minimize C transpose X, let's say subject to X in some polyhedron, and you can assume for now, let's say it's some constraints, it doesn't matter really the form. So maybe actually I don't even have to write this down. So given an LP of this type, okay, if so suppose P as at least one extreme point, okay, which means that it does not contain a line. So of course P is a polyhedron, okay. So given a LP, so P is a polyhedron. So suppose the polyhedron P has at least one extreme point, okay, and there exists an optimum solution. There exists an optimal solution. Okay, remember LPs can have unbounded solutions, right? You can go off indefinitely. Okay. So suppose so for example, if I take a LP of this type, you can have directions in which you can be unbounded. Okay. So suppose you have a problem where this polyhedron has an extreme point, which means it does not have a line. And this optimal value is finite. Okay. So that means there exists some optimum solution. Then what you can claim is then there exists an optimal solution at an extreme point of P. Okay. So what this is saying is what we have seen before, which is you are somehow in at least in two dimensions when we are moving the lines parallel to itself and looking at the objective, we see it's at a corner point or a basic feasible solution. This is just making that concrete. So you can restrict the if there is an optimal if the polyhedron has an extreme point and there is an optimal solution to this problem, which means that you don't have unbounded things happening. Things are not unbounded in some direction where the objective function is minus infinity, for example, and clearly it's feasible. Then there exists one solution which is an extreme point of this polyhedron. Okay, so we're going to argue this because this will help us in the algorithms to just focus on extreme points or BFS or vertices. Okay, so what we'll do is so we are going to again, just to keep it simple, let's suppose this was the polyhedron. Okay, let's say this is a polyhedron, let's call this P. Okay, so suppose V star is the optimal value. So let's say V star is the optimal value of the LP. What I mean by optimal value is you solve the linear program and you find the objective function. Okay, what is the optimal value? Okay, so I'm going to now define a new set, which is let Q be defined as all x such that x lies in P. Okay, and the objective function at the points x is equal to V star. Okay, so remember V star is a fixed number now. It's an optimal value. Suppose I solved the LP and I found the optimal objective function was, let's say, 10. Find all points which give an objective function of 10. So for example, if I take this, let's say this is my polyhedron, let's say my objective function is increasing in this direction. Okay, then my optimal solutions are what? This set Q are all these points. Okay, it's basically this line. Okay, so basically Q is a set of all optimum solutions to the LP. So what we want to argue is, okay, fine. So what do we know about Q? So firstly, Q is clearly contained in P, right? This is obvious because it's all points in the polyhedron which have a particular objective function value, which is attained. Since P does not contain a line, so P has an extreme point. Since P does not contain a line, Q also cannot contain a line. It's a subset, right? If a larger set does not have a line, a smaller set cannot have the line. Q does not contain a line. Okay, that means that Q has an extreme point. Therefore, Q has some extreme point. Okay. So in this example, these are the two extreme points for Q in this example. Okay. Q, the larger set has some extreme point. The smaller set also has to have an extreme point because the larger set does not have a line going through. Smaller set cannot. Okay. Fine. So all we have to argue now is that every extreme point. So we will claim that we will show that every extreme point of the smaller set, every extreme point of Q is an extreme point of P. And this will prove the result. Why is this? Because Q is a set of all optimum solutions. So what is Q? Q is a set of all optimum solutions. That's Q. If every extreme point of, and we know Q as an extreme point. If every extreme point of Q is also an extreme point of P, then we are obviously, because all these points are also the optimum, the original problem has the original, there's an extreme point of the original polyhedron, which is optimum. Is that clear? Yes or no? Like, yeah, clear? Okay, fine. Okay, so let's, so we'll do this by contradiction. So let X be an extreme point of Q. So remember Q has extreme point. So let X be an extreme point of Q, but not of P. So we'll do a contradiction. So we'll argue this cannot happen. Okay. So what does it mean for X to be an extreme point of Q, but not of P? This means that exists two vectors. Again, this is why you have to be comfortable using different definitions. So that exists Y and Z, Y not equal to X, Z not equal to, so there exists Y and Z both in P, Y not equal to X, Z not equal to X, and some lambda and 0, 1, such that X can be written as a convex combination of these 2 points. Okay, because I'm assuming that this point X, so X is an extreme point of the smaller set. Okay, this set Q, optimum solutions. This point I'm assuming is not an extreme point of P. So I'm assuming, for example, let's say this is an extreme point. I'm assuming this is not an extreme point of the larger set. I'll prove this cannot happen, or we'll prove it cannot happen. These are the 2 extreme points of Q. Suppose it was an extreme point of Q, but not an extreme point of P. We'll create a contradiction. Okay. That means you can find 2 other points in P which are such that X can be written as a convex combination. Okay. Now, what do we know about the objective function? We know that V star, because X is lying in Q, V star is equal to C transpose X, which is C transpose lambda Y plus 1 minus lambda Z. Okay. Also, furthermore, because Y and Z lie in the set and V star was the optimal value, clearly V star has to be less than equal to C transpose Y and V star has to be less than equal to C transpose Z. V star is the optimal value. These are feasible points in the polyhedron P. So V star has to be a lower bound on the objective function of these 2 points, evaluated at these 2 points. Okay. But if V star is equal to these 2 numbers and V star is term by term less than equal to each number, the only way this can happen is this implies V star has to be equal to C transpose Y and V star has to be equal to C transpose Z, because you've got this equation and these 2 equations. The only way, this term is lesser than this term. Take out the lambda, okay? This term is lesser than this term, but it is also equal. Only way this can happen is term by term, it has to be equal. Otherwise, this cannot happen, basically. Okay. Which means that this has to satisfy, which means, therefore, Y and Z also lie in the set Q, which implies Y and Z also lie in Q, then X cannot be an extreme point of Q. Then X cannot be an extreme point of Q, violating our assumption. So it's a proof by contradiction, sorry. Then X cannot be an extreme point of Q, completing the proof. Okay. So all we are doing is we are saying that you can write it as a convex combination of some points in the larger set, but each of these points you can they also have to lie actually in the original set, optimal sets, which means X cannot be an, we assumed X was an extreme point, which means I cannot write X as a convex combination of 2 other points in Q, which are different from it, but we just did, which means this is not true. It cannot be an extreme point of Q, but not be an extreme point of P. Okay. So again, this is proof by contradiction. But the useful thing here is it says that what is important here? There exists an optimum solution at an extreme point of P. Okay. This is important because simplex will, we can now restrict attention to these points. Okay. Good. Any questions with this? Any any clarifications, any comments? Again, uh, you will have to spend some time on your own going through the proofs later on. I know I'm doing it in one shot, and you need some time. Okay, I mean, so you have to go. I mean, if it's spend some time with the proofs on your own to go through the logic. Okay, and if you have questions after that, you can ask me at the next class, or if you have questions, you can ask me right now. Okay, fine. So, are there any? Okay, so we are going to. So next class we will start searching for these. I mean, we know we have to find basic feasible solutions. We have to find the best basic feasible solution, and we will look at the simplex method for doing it. But for this class, I want to mention a couple of other things about polyhedron more broadly, which are useful. Again, I'm picking up topics which I've found to be useful. Having worked in this area now for some time, you will read papers on different topics, and some ideas will you will see ideas which show up in other areas about polyhedron, and so some of these ideas I find relevant and useful. So I want to mention a couple of other things for today's class, but simplex will be next class. Okay. So the next concept which I want to cover is the notion of projection of sets and projection of polyhedron. Okay. This is an important idea. So we're going to talk about the projection of polyhedron. Of course, we are doing polyhedron because we are in the LP space, but you might be interested in projection of sets more broadly. Okay, because these are, when you do optimization, this becomes important. So I want to define the projection, and I want to define an algorithm which will help you find a projection of a polyhedron, which is a useful algorithm to know. Okay. Okay. So let's first define what a projection of a polyhedron is. Okay. So given a polyhedron P, okay, so we're going to start by making a projection onto a single. So I'm going to project out a single coordinate. So the projection on the first n minus 1 variables, okay, is defined as, I'll show you an example after we do the definition. So I'm going to define the projection on the first n minus variables of P as what? Take x1 up to the xn minus 1. All x1 to xn minus 1 such that there exists some xn such that this x1 up to xn lies in P. Okay. So this is a definition of a projection of course, actually, this is a definition of a projection on any set. But because I've defined a polyhedron, so this is a polyhedron. Okay. But if you have some other set, of course, it's just a projection of a set. Okay. How does this look like? What does it mean? Okay. So in 2D, it's easy. But let's do maybe in 3D. Okay. I'm not going to be great at drawing this, but let's try. Okay. So think of something like a tetrahedron, but maybe the tetrahedron is a bit tilted. Okay. So I've got a triangular base, let's say. Okay. In 3D. Okay. So let's say this is x1, this is x2, and this is x3. Okay. So I've got a triangular base, a tetrahedron, there's a point on top. Okay. So it's a triangular base pyramid, except this point in the top, it's not in the center, it's outward pointing. So imagine that this lies somewhere outside the tree. No, so if I take these 3 points and just take it up, this top point is a bit tilted. So it goes out a little bit. So this point, okay, is a bit outward. Okay. It's not inside this triangle if you take it up. Okay. So just imagine it's pointing outwards. Okay. So now this is P. Okay. All points in the set is P. Okay. I want to project this set down onto the first two coordinates, x1, x2. How will it look? This triangular base, so this part will remain the same. This part will remain the same. This triangular base, the third part, the third side of the triangle at the base, if I've got this point going out a little bit, when I project it down, that point actually will take this out a little bit. So it will squash. I mean, hopefully you can visualize this, but there'll be some squashed form of this top part. Okay, and this triangle, this third side will be within this region. Okay, so this is the projection onto the first two variables of P. Is it clear? I mean, you'll have to visualize a bit, but just think about, take a set. What does it mean? Basically, it takes, if I take a point here, what does the projection mean? If I take a point here, I can find a point here where it's where I mean I can find a x3 so that I can find a point in the set. If I take a point here, this point, for example, this point here will be this point on top. Okay. So it'll be, so this part of the region will be slightly squashed in, basically. Okay, if you're able to visualize it. Okay. If you want to now project this set, let's say onto the x one, so I want to project out, let's say x 2. So I want to project it onto x1. How will it look? So if I take this set and project it onto x1, it will simply be this part, right? So this part will be this part will be this. So from here to this line, from here to here, will be this part. So this will be the projection onto, so projection 1, projection 2 of P. Okay. So if I try to project this, basically, if you want, I mean, essentially, if I project this onto this space, it will be these values, basically. Is that clear or no? Is the definition of projection clear? If I'm projecting this set onto the x1 variables, it will be all these x1 values between this and this. Okay. You just take this point. This is not very well drawn. Just 1 minute. Yeah, sorry. Is the projection of this set. In fact, if it, so projection of the projection is actually the projection of the original set too. So if I want to project this only onto the x1 variable, it will be this set, basically. Because the projection is the operation will, projection of the projection is the projection of the original set. So I can project onto, there are many, I mean, you have written the projection onto just, I'm projecting out just one variable, but in principle, I could project on any set of variables. Okay. I'm just doing it for one variable to keep it simple at this point. But you can, I can give you 100 variables and I can say a set in 100 variables. I say on the first 25 variables, I want to project out the set. So I have to find remaining 75 variables so that for every point in this projection, that is some value of points in the 75 other variables, so that that point exists in the original set. That's what it means. Okay. Now, this is an important object because it will turn out that the projection of a polyhedron is also a polyhedron. As we have seen, this is a polyhedron in dimension 3. The projection is a polyhedron, is a set polyhedron in dimension 2, which is a projection in dimension, a polyhedron in dimension 1. So we'll prove this, but towards this, we'll use an algorithm. So we're going to look at, so how do you find projections? Okay. So we're going to look at this algorithm called the Fourier-Motzkin elimination algorithm. Okay. It's a simple idea, but it's a useful idea to know. So this is an algorithm to, so given a polyhedron, so this is for polyhedron, given a polyhedron P, let's say x in Rn, ax less greater than equal to b, we eliminate a variable xn, okay, and construct the projection of P onto the first n minus 1 variables. Then you can repeat this, repeat it till we go to a single dimension. Okay, so the idea is what I just showed you with a figure. You keep doing this projection step by step. That's the Fourier-Motzkin elimination method. I'll show you how to do that next. Okay, so there's an algorithm which you can do given inequality constraints, which can do this. So I want to just discuss this algorithm. It's a useful way to project out. It's not particularly very efficient, but it's a useful method to know, and it's conceptually quite elegant and understandable. Okay. Okay. So let's discuss the algorithm. So I'm going to give you the Fourier-Motzkin elimination algorithm. So what we're going to assume is X in Rn, and I'm going to write down the specific form. So Aij Xj greater than Bi for I going from 1 up to M. This is my polyhedron. So I give you a set of linear inequality constraints. If it's equality, I'll make it linear inequalities. That's fine. Just double the number of constraints. That's my polyhedron. I want to I want to find the projection onto the first n minus 1 variables. How do we do it? Okay. So the algorithm goes as follows. So this is the Fourier-Motzkin elimination method. So step one, okay. So look at we are interested in projecting out the xnth variable. Okay. So there are m constraints. Each of the constraints will have a coefficient aim, ain corresponding to the nth variable, right? Is the last column of the A matrix. Okay. So we're going to define three sets depending on the signs of this. So define three sets. S0, which is a set of all indices, all constraints such that ain is 0. Okay, so remember my A matrix. I'm just looking at the last column of the A matrix. These are my ain. Find me the constraints where the indices are, the coefficients are 0. Find me the constraints where coefficients are strictly positive, and find me the constraints where the coefficients are strictly negative. These sets might be empty sets, but you can find these sets. Okay, you just partition every set into one of these, every constraint into one of these three sets. So if you look at S0 union S plus union S minus, this will all the constraints will be captured in one of these sets, and these sets are disjoint. Okay. Okay. So we're going to just rewrite the constraints a little bit. Okay. So what happens if a variable ain is 0? If xn, that means xn does not show up in that constraint. So it's a constraint. Let's say it's a variable. I've got a problem in 10 variables. I've got a constraint where the 10th variable is not showing up in that particular constraint. So for every constraint in S0, so for all I in S0, I can rewrite the constraint simply as it's just summation j from 1 up to n minus 1, aij xj is greater than equal to bi. Okay, why is this? Because ain is 0. So last term is 0. So I'm just writing the constraint again, except identifying that ain is 0. For every I which is in the positive, where the coefficients are positive, I'm going to write the constraint only in terms of xn on the left-hand side. So it's ain times xn, and I will divide by ain. Okay. And because ain is positive, my sign will still remain as greater than equal to. So all we are doing is we are writing this constraint as xn greater than equal to bi by ain minus, I've taken the remaining n minus 1 terms to the right hand side, aij by ain xj. So I'm just rewriting the constraint, just dividing by ain, and because it's positive, the sign will remain greater than equal to. Is that clear? Likewise, for the constraints where AIN is negative, so it's like minus 5 times xn is greater than some number. If I divide by minus 5, the inequality will change in sign. So I will get this constraint. For all these constraints, I can rewrite the constraints as okay. So we're just rewriting the constraints separately for each of the three parts. Okay, they are just equivalent ways of writing the same constraint. Now, if we think about the first set of constraints, so I'm going to call this star, all these three constraints. If you think about these constraints do not involve the xnth variable. You're right. This should be n minus 1. Thank you. This should be n minus 1. You're right. It should be n minus 1. You're right. Thank you. For the first set of constraints here, there is no xnth variable. For these constraints, there are upper bounds on the xn variable and lower bounds on the xn variable. So what does the method tell you? The Fourier-Motzkin method say, you will, these upper bounds, so you will write the poly, so we're going to define in step 2, we're going to define a polyhedron Q as follows. So polyhedron Q in n minus 1 variables. So initially it was in n variables. As I will keep the first set of constraints as is. So I will not take that out. I'll keep it as is. The second set of constraints gives me upper bounds and lower bounds on the xnth variable. So for the projection to be valid, the upper bounds have to exceed the lower bounds, basically. So what we are going to do is, we're going to rewrite this as, so bi by AIN minus summation j from 1 to n minus 1 aij by AIN xj. So this lower bounds. These are the upper bounds. I'm going to write this now as bk, just to be clear that there's a different index. Bk by akn minus summation j from 1 to n minus 1 to n minus 1 akj by AIN xj for what? For every I in S plus and for every k in S minus. So if I give you 5 constraints here and 3 constraints here, I will write 5 into 3, 15 constraints. So I take every lower bound, every upper bound has to be exceed the lower bound. So this is a set. This is a set involving n minus 1 variables. There is no, the xnth variable has been projected out. Okay. Is it clear what we are doing in the algorithm? The claim is, so the theorem is, the polyhedron Q returned or constructed. So that 2 steps is the Fourier-Motzkin algorithm, okay? Elimination method. Constructed by the Fourier-Motzkin. So of course, the name of the people who, the Fourier-Motzkin elimination method satisfies. So Q is exactly the projection of P onto the n minus 1 variables. Okay. So it's just a simple set of operations. You just divide this into 3 sets when the coefficients are 0, positive, or negative. And then I just normalize out the coefficients. For 0 ones, anyway, it doesn't exist. If it is positive, I divide and I make it 1. If it is negative, I also divide, but the inequalities will change inside. So some will give me upper bounds, some will give me lower bounds. I have to ensure that these upper and lower bounds, in terms of the n minus 1 variables, I have to satisfy. They have to be valid. That means the upper bounds have to exceed the lower bounds. So by doing this, we claim that the corresponding polyhedron is actually the projection. Okay, so this I'm going to call this star, double star. Okay, so this set is exactly the projection. Okay, any questions with this? Do you want to do an example before I do the proof first, or is the algorithm clear? Okay, is the algorithm clear? Okay, I'll do an example first, and then I'll prove the algorithm, the result. So let's do an example just to be clear what the algorithm is doing. Okay, so let's take the same. So let's take the following example. Okay, so let's take the polyhedron. I won't maybe I won't do all the steps. I'll just show you a couple of steps, and you can try it out on your own. But let's do this. X1 plus x2 less than equal to 1. X1 minus 2x2 greater than equal to minus 2. X1 greater than minus 2. X2 greater than 1.2. And x2 greater than equal to minus 2. I'm giving you some polyhedron in 2 dimensions. Okay. So let's just plot this out. Okay, so this is x1, that's x2, x1 plus x2 less than equal to, so x1 plus x2 less than equal to, is it 1? What I've got, x1 plus x2 less than equal to 1, yes. So that's, okay, maybe you can do the geometry on your own. Okay, I'll do the algebra here. Okay, you can plot it on your own later. Okay, let me just do the algebra here. Okay. Okay, so let's apply the algorithm. So I want to project P onto the first variable. Okay, space. So I want a constraints in x1 space. Okay, so let's look at this constraints. Okay, so so this P is what? It's basically, okay. So I've got x1 greater than 1 minus x2. Okay, intuitively, what is it doing? I'm just going to write everything in terms of. So actually, I want to project this onto. So I want to take out x2. So let me. So x2 is less than 1 minus x1. Okay, this uh, x2. So 2x2 is less than equal to. So x2 should be less than half x1 plus 1. This is the second constraint. Okay. So x2 is less than equal to 1 minus x1. Okay. X2, if I take it this side, okay, 2x2 is less than x1 plus 2. So x2 is less than half x1 plus 1. Okay. This is x1 greater than equal to minus 2. Okay. There's no x2 in this constraint. Okay. x2 less than equal to 1.2 and x2 greater than equal to minus 2. Okay. Now we'll start projecting out. Okay. So how are we going to create Q? Okay. So far, so Q is going to be defined as, so I want to find this. Okay. So the way we are going to do this is Q is going to be all x1 such that you take the the constraints which don't involve x2, you keep that in. Okay, so x1 greater than equal to minus 2. Okay, don't change anything there. Look at the parts which involve x2. There are two upper bounds, or rather three upper bounds, and there is one lower bound. So all we have to do here is we have to say 1 minus x1 is greater than minus 2. Upper bound is greater than equal to lower bound. Okay. Half x1 plus 1 is greater than minus 2 in this example. Each of this upper bound, and 1.2 is greater than equal to minus 2. This is a trivial inequality. Okay. This will give you a range. Okay. So if you can write this out, it's x1 greater than minus 2, x1 less than equal to 3. Okay. This is x1 greater than equal to -6, I think. Okay. And last one is just a valid inequality. So this, so if you, again, you can check this on your own, but this should give me x1 between 3 and -2. Okay. Check this on your own if this is right. I mean, I could have made some small mistake in my calculations, but that's a projection. But hopefully the idea is clear. You find valid upper bounds and lower bounds. Make the upper bounds greater than lower bounds. In this example, there are 3 upper bounds and 1 lower bound. So it's for every upper bound, you put the lower bound. If there were more constraints here, you have to take every combination. Okay. Okay. So is that clear? And you can check the projection, you can do the plots, and you can check on your own time if I made any mistake, and you can try plotting the region. Did I make some calculation mistake somewhere? Where?
Sorry.
There are 3 upper bounds and there are 2 lower bounds, but this lower bound is on x1. Okay. So it doesn't force anything on x. So I'm trying to project out x2. So I'm trying to figure out what I know about x2 in terms of x1s and putting those constraints. So this constraint I've got to keep in. Okay. So this is like the S0 constraint. So in my index set, I've got these S0 set, right? That's like my S0 set. S plus and S minus. S plus are these basically like the 3 sets here, and there's 1 set here. Okay. Okay. So let's just do the proof here. Okay. Proof. Okay. So I think the proof is reasonably straightforward. Okay. You got these sets. Okay. This set star is just writing the original constraints in terms of xi's and xn's. In double star, I'm taking out the xn constraints. Okay. So to argue that, so are the 2 sets clear? The set star and double star? Set star is just rewriting the constraints. Nothing has changed. Set double star, I've taken these upper and lower bounds and made the constraints only in terms of n-1 variables. Okay. So we'll prove this in 2 parts. Okay. So you can argue that Q. So let's maybe first start by showing that the projection of n-1 P is contained in Q. Okay. Why is this the case? So given some point, so what do I want to show? I want to show any point in this set lies in this set. So given x1 bar up to xn minus 1 bar, okay, the projection is in n-1 dimensions. Okay. Suppose this lies in the set projection of n-1 P. Okay. What does it mean? It means that then there exists some value xn such that, so given any point in the set, this is the definition of a projection. If I give you a point in the projection, I can find some point xn so that it lies in the set P, right? Okay. This point, so this point x1 bar, these values x1 bar up to xn minus 1 bar and xn, since they are in P, they have to satisfy this constraint star, because this is just a rewriting of the constraints P. Okay, I'm just rewriting the same thing. So this point has to satisfy star. It's the definition of a projection, and obviously there exists some point value xn, and since I'm just rewriting the constraints in star, it just satisfies them. But because they satisfy star, any point which satisfies this constraints, so if I've got xn which is less than or equal to this number and xn is greater than this number and less than this number, because they satisfy both constraints, the upper bounds have to be greater than the lower bounds or greater than or equal to. So clearly, double star, okay, which means that hence this also lies in the projection. Okay, again, it's relatively straightforward, but hopefully it's clear. Okay. For the other direction, you want to show Q lies in the projection of n minus 1 p. What do? You take a point, you take, so given some x1 bar up to xn minus 1 bar in Q, okay, clearly using so if this point satisfies Q, what is Q? Is given by these star constraints, right? So these constraints, the first set of constraints here are exactly the constraints in the polyhedron. These upper bound and lower bound constraints, okay, the for every I and for every k, the upper bound is greater than the lower bound. So the largest of these numbers has to be lesser than equal to the smallest of these numbers. Okay. Every term by term, the upper bounds are greater than lower bounds. So the largest value on the left-hand side has to be lesser than the smallest value on the right-hand side. So if I maximize this over I and S plus, and the minimum over S minus, it has to be true that the upper bounds have to, be, just be careful with the indices, but it's not particularly hard to do. Uh, Essentially, this has to be true because the upper bounds, this for every I and for every k. Okay. So what do you have to do? You have to just find a value which we just choose. We choose xn bar to be a value, to be any value in this uh, uh, between this upper and lower. This is a lower bound. This is an upper bound. Upper bound is lesser than greater than lower bound. So there's a number, right? Let's say 5 and 3. Choose any value between 3 and 5. Choose any value in this range, basically. Okay. Then this xn bar will satisfy the two constraints here, basically. Sorry, I went all the way back. It will satisfy these constraints. Okay. So the proof is relatively straightforward. You can look at it. Okay. I'm just constructing a point, basically, which satisfies the conditions. Okay. Okay. Do you want me to go through this again? Is the algorithm clear? Okay. So not everything is rosy with the algorithm. Okay. So note, so we can, so applying the algorithm can lead to many new constraints being added. Okay. And this is actually an astronomical sum. Let's look at this. So let's say I started with n constraints. Okay. What happens in the algorithm? I look at the sets with zeros, positives, negatives, and then based on the zero constraints remain the same. The positive coefficients I create, positive and negative coefficients, I create upper and lower bounds, basically, right? So imagine the worst case. I might have n by 2 constraints giving me upper bounds and n by 2 constraints giving me lower bounds. So after one round of this algorithm, n by 2 constraints on this side, n by 2 constraints here. Every pair I have to take and I have to create upper and lower bounds, which means that this will give me after one round, in the worst case, I will have n by 2 into n by 2, which is n squared by 4 constraints. This is a worst case analysis, right? I give you 100 constraints. Maybe 50 constraints have positive signs for AIN and 50 have negative signs. So I'm now going to create for every pair, I'm going to create an a linear inequality from the upper bound and lower bound constraints. That's 50 into 50. Okay, that's 2500. I repeat this. I've got n squared by 4 now in the worst case. This is worst case analysis. Okay, it'll become n to the power n squared by 8, n squared by 8. So it's like n to the power 4 by 64 constraints in the worst case. Okay, this is second round. So after d rounds of this algorithm, you keep projecting out a variable. Roughly, this will be order n to the power 2 to the power d. Okay, this is horrible complexity. Okay, this is a not only, I mean, this is growing extremely rapidly. Okay, it's not 2 to the power n. It's n to the power, if d is n, n to the power 2 to the power n. So this is doubly exponential, not only single exponential. Okay, so it's not particularly a very efficient algorithm. In fact, it's a pretty uh, doubly exponential. So it's not an efficient algorithm. Okay, but it is an algorithm, and you can do it at least for a few rounds. You can do it. Okay, so that's one thing which you should keep track of. Okay. Any questions there? Again, I'm just giving a rough analysis of how big the size can grow. It can grow very rapidly. So you can be generating. I mean, clearly, if you think about it, ultimately, if I bring it down to a single variable in one dimension, a polyhedron in one dimension is what? It's an upper bound and a lower bound. Ultimately, it's an interval. Okay. So only two constraints you need actually. So it's going to generate, the algorithm can generate many redundant constraints which are not adding much value basically. Okay. But you don't know beforehand which upper bound and which lower bound to take. You don't know this basically. Right. Okay. So that's the first claim. The second note is, observe that this Q is given by, the projection is given by these constraints, which are linear constraints in the x1 to xn minus 1 variables. What does this mean? It means that the projection of a polyhedron is also a polyhedron. Because I took a polyhedron in n variables, I gave you an algorithm which gave you a projection, which is a set of linear constraints in n minus 1 variables. So it implies that if you take any polyhedron, the projection of any polyhedron is also a polyhedron. I mean, it might be a trivial, I mean, it might be obvious in your mind, but to argue it, the algorithm shows you that this is true because it created a new polyhedron which has finite constraints, finitely many, and which are linear constraints, is also a polyhedron. Okay. More generally, if I give you a so more generally, if I give you a given a polyhedron P, let's say in n plus q variables. Okay. Okay. So imagine that there are variables x and y which lie in P. Okay. So x is a set of first n variables, q is the set of next q variables. Okay. So the projection of P onto the x variables is the set of all x such that all x in Rn such that there exists y. I'm just defining a more general projection such that xy lie in P. Okay. So again, this is a useful definition to know. This is a general. This is a definition of uh, a general projection. Okay. If I give you a set and I want to find the projection onto a subset of variables. Find me all the points so that for every such point, there might exist some point y so that x comma y lies in the set P. Okay, that's the definition of a general projection. Okay, I'm just defining it not, yeah, not only in one variable, but in many variables. Okay, questions at this point about the Fourier-Motzkin elimination. So what we said is a projection of a polyhedron is a polyhedron. That is an algorithm which can do this. The algorithm is not particularly efficient, but it is an algorithm. And there are other algorithms you can actually implement. Okay, but this is a useful algorithm to know at least, and it's relatively intuitive. Okay. Okay. There is one final topic I want to cover uh, before we start on simplex. But do you guys have energy for 5 or 10 more minutes, or shall we do it next class? If you're tired, we can do it next class. No problem. Are you mentally exhausted? You want some? Okay. I will take your word for it. I can ask you questions. We are covering quite a lot of ground. Okay. And like I said, the best way is to go back and read on your own. Okay. And then you will work through the logic at certain steps, and steps will be clear. Some steps may not be clear. You can come back and ask me why you did this or how did this happen or not. If it is clear, great, but you will have to spend time on your own. Okay. That's the best way to learn the subject. Okay. My goal is to point you to the what I think are important ideas. Then mastery on the subject will come down to you studying on your own, basically. And you ask me questions, of course. Okay. Queries, clarifications, whatever. Okay. Okay. Are there any questions online for the audience? Okay, if you've got questions, you can ask me. Otherwise, we'll call it a day and we will meet next Wednesday. I'll be happy to answer any other questions. Okay. Otherwise, let's stop for today.